Hello, Math 1224. This is Dr. P with Lesson Launch 18.1. Can you calculate this? In this video and the next one, I think we're going to have only two videos this time, and I'm hoping they can be pretty short. So let's keep our hopes up. In this video, I'm going to share with you an interesting new trick for calculating things that you probably didn't know before you took Calculus 2. So my guess is that prior to this course, you may have had some experience calculating sums of infinite series, but only if those infinite series were geometric series, and of course only if they were convergent. And even then, you might not have had that experience prior to calculus. If not, that's fine. Now you've had it. But now we're going to broaden the collection of infinite series whose sums we can calculate exactly. All right, and we're going to do that with this example here. Now this looks interesting. Who knows what's going to happen with this? But let's just first write down, just as a sense-making method, let's write down what the first few terms of this series would be. So this would be 6, because 0 factorial is 1, and then 1 factorial is 1, so that's 12, and then 2 factorial is 2, so that is 24 over 2, that is also 12, and then 48 over 3 factorial, that's 48 over 6, that's 8, and then 4 factorial is 24, so this next term would be 4. So I don't know, maybe the terms are starting to get smaller. It's kind of hard to tell. They're behaving sort of erratically for the first few terms of this series, but those are the first few terms. But I claim that actually this series does converge, and we can find out exactly what its sum is. Isn't that crazy that one could be able to do that? But here's how we do it. We start by doing something that I like to call backing out. So we're going to back out of this particular calculation and try and generalize what's going on in this series, and then we're going to generalize some more, and then once we're up at about 30,000 feet above sea level, we should be able to see what's happening with this series, what this series really is. And you might already have a clue, because you'll notice that there are some denominators of 0 factorial, 1 factorial, 2 factorial, 3 factorial. Well, anytime that happens, there's a pretty good chance that what you're working with is some kind of Taylor series. It's a Taylor series of something instantiated for some particular value of x, and that's exactly what it's going to turn out to be here. So we're going to back out and first try to write this infinite series in sigma notation. That is using summation notation. We're going to try and write that in sigma notation. And then number 2, we're going to try to view the whole thing, once we've done that, as a Taylor series. That's the game plan, okay? So I'm going to back out here, literally back out or zoom out, so that we can see what we are doing here, okay? So first we have to do a little bit of algebra to figure out how we're going to write this series in summation notation. Now, let's just put together the parts that we think we can put together right now. We might have to adjust later. That would be okay if that happens. But one thing I know is that I have a term for every natural number, including 0. By the way, French people consider 0 to be a natural number. Another reason why maybe we shouldn't emulate the French. But in this case, it's kind of useful. So for every natural number starting with 0, we have in the denominator a k factorial. All right, that alone is progress. So now I just have to figure out how to model, using algebra, this sequence of terms 6, 12, 24, 48, 96, and so on. Well, one thing I notice is that every time I bounce from one term to the next, I am multiplying by 2. I'm multiplying by 2. So one thing that suggests is that, well, this term, for example, this is 6 times 2. And then because I'm multiplying by 2 each term, that makes this 24. That's 6 times 2 times 2. And then the next term is like 6 times 2 times 2 times 2. And I realize that what I'm doing probably seems kind of elementary, but if you learn to write calculations this way, that is, leave some things uncalculated, rather than having them in fully simplified form, you can actually get a lot of useful information or insight about how the terms of a sequence are behaving. See, look at this. What is that really? That's 6 times 2 to the third, and then the previous term was 6 times 2 squared. So anyway, if we know that, if we know all of that, then we can write the kth term of this as 6 times 2 to the k. So this is really 6 times 2 to the k over k factorial. Sorry, this is... you'd think that if I'm on a tablet, I might have a little bit better board hygiene than if I were on an actual chalkboard in the middle of class, but you'd be surprised. I can screw up any workspace. But that's what I seem to be working with. Okay, so that's what I'm referring to by step 1, is try to get this thing in sigma notation. That is, get an index of summation in there and write down the general term. And by the way, every time you do this, one thing you should be doing is you should be checking my work. That is, go back to this and make sure that what I've written down here in sum notation, make sure that that is consistent with and actually produces these terms. Okay, have you done that? You can pause the video if you want to. All right, well, anyway, I'll go on. Okay, so that's step 1. And now step 2, different color now. Step 2 is I'm going to try and think of this as an instance of a Taylor series. Okay? Actually, I guess if I'm drawing arrows, sorry, speaking of board hygiene, I guess the arrow should go this way. Anyway, I want to think of that as some kind of Taylor series. Now, I don't know of any Taylor series that goes 6 times 2 to the k over k factorial. Taylor series tend to have variables in them, a variable like x, not just the index of summation. But what if I thought of this as, well, the 6 is not really a variable, so I'm just going to leave that as a 6. And then think of that 2 as an x. See, if this is going to be a Taylor series, it has to be a power series, so that I've got to have something with a variable raised to the k in there. And then I'm still over k factorial there. Now, does that look a little bit more like a Taylor series? I certainly hope so. Because if I were to pull out this factor of 6, which is in every term, so I can just pull that out by the distributive property. I guess it's like an infinite distributive property. I'm not sure we've actually formalized that, but that's totally a thing. Just trust me for now. Now this should be starting to look very familiar. This is, in fact, the Taylor series for 6 times, what is that? That's e to the x. It's 6e to the x. So what I have up here, what I'm looking at here, this is, this is 6 times e to the x when x equals 2, which means that should be 6 times e squared. Now, I don't know off the top of my head 6 times e squared. That's and I don't have a calculator in front of me, but e is about 2.71 something, like 2.72 roughly. So e squared is like, I don't know, it's a little bit over 7. I'm going to say 7.3. That's probably a little bit wrong, but I bet it's not a lot wrong. So that means this would be about 43.8, 44. Let's just, make it a nice round number. And I can actually check whether that seems reasonable in light of the little napkin calculation I did at the beginning. I had 6, 12, 12. Let's just tally these up. 6, 18. 18 plus 12 is 30. 30 plus 8 is 38. Oh boy, running out of room here because I'm hoping to get a sum of about 44, and I'm already at 38. And then I add 4 and I get 42. Oh mercy. Am I going to have enough room? Well, the next term is so I'm at 42 right now. The next term is what is that? It's 192 over 120, which is that's a little over 1.5. So now I'm up to about 43.5. And now you got to be thinking, oh man, there's no way this is going to work out because I said 43.8. Now actually, I will confess, I stopped the video for a moment because I was getting a little bit worried. And I calculated using Wolfram Alpha 6e squared. It actually comes out to be about, not 43.8, 44.3. I did say about 44, so you got to give me some respect for that. 44.3, though, is about where we were going to be. That next term, that fifth term, k equals 5, takes us up to about 43.5. And then after that, it's a miracle. The terms actually start getting very, very small quickly. The next term is, I think it's some 384 over 720. That's about a half. And then after that, they just get smaller and smaller. So actually, it turns out this is a very reasonable estimate for this sum. If you want something that's not an estimate, that's the actual value of the sum, this is it, 6e squared. That is the sum of this series. What a trip, right? That you can add up all these rational numbers and wind up with a sum of 6e squared. But if you believe that this is a Taylor series, this right here is a Taylor series for 6e to the x, if you believe that, and I didn't hear anyone complaining the other day, then you really do have to believe that if you were to substitute x equals 2 into this, then that's equivalent to substituting x equals 2 into this. And that's exactly what this series is that we're working with. So anyway, that's an example of the technique I'm illustrating. I'm going to do one more example of this, and then in class we're going to have a presentation on how to build more Taylor series. So stay tuned for one more video.